Hello, I'm back once again. Once more time, I'm Mr. Steele. I'm here to work through another video in the Essential Skills Quiz Model Series for Honors Pre-Calculus's first half. And in this video, we're going to be working through the fifth of those questions on the weekly, or more or less weekly, Essential Skills Quiz, which focuses on evaluating expressions involving logarithms. So just as I have in each of the videos so far in the series, and that most of the videos that follow will contain as well, I'm going to give you some brief background by talking about some key ideas or some of the fundamentals of this idea of logarithms first. Then I'll go through and work through each of the questions that appear in your ESQ model. So that way you've got a little bit of extra support if you're looking for it, to kind of figure out how to navigate those questions, to get them right, to improve your grades, and to solve and achieve world peace. That's the hope anyway. So, well, if world peace is on the docket, let's not waste any time. Let's kick this thing off, huh? Why don't we? So as I said, the first place I want to begin is by talking about just a couple key ideas to the logarithm concept, just some things that I think will help sort of get you into the right place to attack this question specifically. Obviously, logarithms tend to be a huge unit in Math 3, or if you're taking the accelerated class in that portion of your course. But at the same time, there's three specific pieces that are really relevant to what you're going to be facing in this particular question. And I'm going to try to hit everything from those three sections as broadly as possible, but also in an efficient, quick manner as well. So to kick things off, the first thing to note, just as kind of a foundation for logs, particularly if you're someone that's like, yeah, I remember doing logs, but I don't remember anything about them, a good place to begin would be just to remind you sort of where a logarithm comes from. And it all comes from the fact that logarithms are the antithesis, basically, to exponentials. They are basically accomplishing the same thing, but in reverse. They are inverse operations in a sense, assuming that the bases are the same. So when I say the exponential definition, what that's coming from, or where that's coming from, is this idea that if you have a log expression, like log base b of x, and that's equal to some y, we'll just use it that way, that is exactly the same as saying b to the y power equals x. Those two things are identical. This is called the biconditional. That's because it's true in both directions. One side is only true if the other side is true. In other words, this is a definition. These two things mean the exact same thing. And that's probably how you remember logs, or maybe how you kind of got it into your head at the very beginning. If I point out that log base 2 of 8 equals 3, you can rationalize that and kind of get your mind wrapped around the concept by pointing out that that's because 2 to the third power equals 8. So in other words, these two things are exactly the same. A log is just a different way of expressing an exponential relationship, but we rewrite it in a different form so that we have that inverse. The same way we don't just write division problems as multiplication. There's something different happening there. It's clearly related to multiplication. Now the second one is very specific to this particular version of a logarithmic expression, because that is what we're going to be doing here. We're just going to be simplifying logarithmic expressions. And it's called the inverse property, and it's something that I don't know that always gets kind of play. I'm not sure it gets its own, definition or title or anything when you're learning logarithms, but it's one of those properties that I think it's really helpful to lean into. And it is a property, meaning that it's true for logarithms, but in particular, it's the inverse property. It's basically a way to recognize that logs and inverses, or exponentials and logs are inverse to one another, how they undo one another when they're put into place. So the place you're going to see it most often on this ESQ model is in this form. We'll have something like log base b of b to the x is equal to x. So the idea here, as you can probably see, is that log base b of b to the x, the log base b and b to the power undo each other, and we're just left with the exponent. So that is one directional version of the inverse property. The other one, which I don't think is going to probably show up when you do the problems on this ESQ, or especially the ESQ model, but is relevant just to kind of put in there, is that the reverse works in a similar way as well. If you have b to the log base b of y, that's going to be equal to y. Once again, it's like these two things undo each other or cancel each other out, and we're just left with whatever's up there. And just as kind of a heads up, so you kind of see where it is that you'll be going with this, you'll see expressions like log base 5 of 1 over, 25 in this question when you're doing your ESQ. And although you may just look at that and go -2, which is great, honestly, you can also think about this as being a starting point to achieve a goal that looks more like this, for instance. In other words, you'd think, okay, 1 over 25, instead of putting b, let's just put 5. And 1 over 25 is 1 over 5 squared, which means this is log base 5 of 5 to the -2 power. And look, there's log base 5 of 5. Those things undo one another, and there we land at -2. So you can kind of see in action what's happening here, or a good way to kind of explain to yourself what's happening when you say log base 5 of 1 over 25 is -2. It's this property taking care of itself. The log base 5 and the 5 to the power, or exponentiation base 5, is undoing, or they're undoing one another. We'll go with that. And then last but not least are the log laws. There are 3 of them that we're going to use, although I suppose in a charitable way we could have called that previous property one of the log laws. But basically these 3 laws will allow us to combine logs together. Now that might not be necessary in a given problem, but sometimes it might be. So I want to make sure that we're all on the same page with the way these work. So for each of these, we've got a way to combine things together. So let's say, for instance, that you start with log base b of x plus log base b of y. That can be condensed into log base b of the product of those 2 arguments, x and y. So log base b of x plus log base b of y equals log base b of x times y. Likewise, you can do the same thing but with subtraction. So log base b of x minus log base b of y. And in this case, obviously, it won't be exactly the same. That'd be awkward. But what you will get is the log base b of x divided by y. And so there is sort of our second version. So again, we have ways that we can kind of condense things down from being multiple logs that are added or subtracted down into just a single log. And then finally, last but not least, this one's a little bit stranger, I think. But if you have some sort of exponent out in front, so we'll go log base, or n times log base b of x, then that can be transformed into log base b of x to the n power. So in other words, that scalar, and this is specifically a scalar, although a function will work too, comes inside and becomes a power of your argument. And again, this will be a way to kind of condense things together, but of course the opposite direction works as well. You can go from a single log down and split it up into 2 separate logs. That works just fine too. So with that in mind, those are the 3 different little, I don't want to call them strategies, those are the 3 fundamental skills that are really going to be invaluable as you dig into the questions on problem number 5 on your ESQ model. So there's your nice background. Let's just go do the problems and see these in action. So to kick things off here, we're going to start with the first problem presented with question 5, which does ask you to evaluate each logarithmic expression. And as a heads up, evaluate does mean they want you to arrive at an answer. We're going to get a numeric value, or at least an expression out of this. And I think for the most part, none of these should have logs left over at the end, although it's possible that maybe there's a version of the standard quiz or the ESQ out there somewhere that I haven't seen that could potentially ask for that. So in this case, we've got 2 pieces to go with. We have log base 4 of 64. And actually, I'll do this in 2 different colors. What the heck? We'll do log base 4 of 64. And on the other side, we'll do ln of e to the 5th. Now, the real strategy here is knowing what the specific approaches to take for each of these. And in truth, in each of these, just so that we have something that's there, although again, I think you could probably potentially do this in your head and get 8 as your answer without doing or showing any work. In this case, we'll illustrate what this actually looks like. So I'm going to use what we called that inverse property. Log base 4 of 64 is the same thing as log base 4 of 4 to the 3rd. And on that other side, ln is the same thing as the natural log, which means it's log base e. E is the number 2.718281828, 45902353. It's something like that. But in any event, it's just a special base for a log that has some special properties that surface later on in your mathematical careers. For us now, like we can just write it as log base e, and then end up with log base e of, and I don't need the parentheses there, e to the 5th. So with that in place, we've now rewritten this in a slightly different way that makes it easy for us to use that inverse property, which says log base b of b to the x equals x. So right here on our first one on the left side, log base 4 of 4 to the 3rd is going to equal 3. On the flip side, we have log base e of e to the fifth, which is going to be 5. 3 plus 5, of course, is equivalent to 8. So there is the inverse property, like deployed to pretty quick fashion, moves pretty quickly through. But again, it's not that you necessarily have to show that work to get there. I'm just trying to be illustrative. I don't know how to pronounce that word. I'm just trying to illustrate for you what's happening underneath the hood if you see someone jump from log base 464 to 3 automatically. This is what's happening. If you can jump all the way to 3 right off that bat, good for you. Aren't you special? Question number 2, very similar problem. You can kind of see the same setup at play here. We've got log base 3 of 1/9, and that's being added to log base 2 of 2 to the 7 W power. So we want to clean this up just a little bit. To help us with that, I'm once again going to separate this out. So we have log base 3 of 1/9, and we have log base 2 of, and it's in parentheses here, 2 to the 7W, just to make that clear. Okay, now, what I'm going to try to aim for, again, even though I can do these in my head, and you probably can too, is I'm going to aim to rewrite the arguments, and by the way, the arguments are the parts on the inside of the log, in such a way that we can use that inverse property. So 1/9, by the way, same exact thing as 1/3 squared, which means I'm going to write that left-hand term as log base 3 of 3 to the negative 2 power. Likewise, we have the log base 2 of 2 to the 7W, and hey, that's sort of convenient. Thanks for helping us out. There it is. Now that we've got both of them there, we can see that log inverse property at play. Remember that property says log base b of b to the x is equal to x. Well, we have log base 3 of 3 to the negative 2. That's going to equal negative 2. And on the other hand, we have log base 2 of 2 to the 7W, which is going to be, as you might expect, 7W. Now the question becomes, how do we clean that up? How do we present that for us? I mean, technically it's correct as it is. The only thing I'd probably do is write this as 7W minus 2, just because that uses the fewest symbols, and there's something catchy about using the fewest symbols. I would argue. Maybe I'm a bad judge. Question number 3 is our final one in this section, and it's not super intense, but there are some elements here that I think are worth addressing just to make sure that we're all on the same page going forward. Important place to be. So the first thing to note here is that we have log base 10, or sorry, it just says log 10. So there's no base. It's not log base 10, that it says at least. But I do have to let you know that this thing, which is called a common log, so log of b, that is equivalent to log base 10 of b. So I believe the origin of that was in our counting system early on. The most common thing to do stuff with was to use your fingers, of which most people have 10. So something along those lines, but I could be misstating what it was or conflating different ideas. But basically those two are the exact same thing. So you can kind of already see here that our second term isn't just log of 10, it's log base 10 of 10. So we'll be able to evaluate that really quickly in just a second. As far as the other term in here, log base 25 of 125, this one doesn't actually resolve really quickly, although again, like most of these, you can probably figure out what it is quick enough. But just to kind of point it out, if we have log base 25 of 125 equals y, then that is the same exact relationship, numerically at least, as 25 to the y equals 125. And at this point, it looks like you're stuck, except we have common bases on both sides. Struggled with that word for some reason a second ago. So in any event, what I mean by us having common bases is that 25 and 125 are both powers of 5. We can write the one on the left as 5 squared to the y, and the one on the right as 5 to the third. Using the power to a power property, we get 5 to the 2y equals 5 to the 3. They both have the same base, so you can imagine log base 5ing both sides to just end up with the equation 2y equals 3. And as you can expect, y then has to equal 3 over 2. So basically this expression up here is equal to 3 over 2. So whatever that was, it's now equal to 3 over 2. All that remains then is for us to evaluate log base 10 of 10. But the power of 10 that gives us 10 is 1, so I don't think it's even necessary to dig deeper into that than we already have. This is just literally log base 10 of 10 to the first power. We can apply the inverse property and get right through it. So however you approach there, though, we end up with 3 halves plus 1 at the end of the day. That's going to be the exact same thing as 3 halves plus 2 halves, which does give us 5 halves as the value of our logarithmic expression. And with that said, that's going to complete our video here. So we were able to work through several examples. So mostly basic, but you can tell you were working through expressions each time. There's no solving here, just evaluating and cleaning up and using some of these log properties in order to get our 3 values. And then, of course, also we went over some key ideas here that are really helpful, and in case you kind of skip through them but do still feel a little confused, I recommend going back and just kind of hearing that brief overview I provided of all that stuff. In the meantime, though, that's going to bring to a close this video. I hope this video was beneficial to you and you're watching, and I hope that it serves you well as you get back into math class really soon. Yeah, hope things are well. Have a great rest of your day.